Now let's have a look at the LTE technology basics. This slide provides an overview of LTE key parameters. First of all, the frequency range for LTE. So LTE can be operated in the FDD and TDD bands of UMTS. So on the next page we will also see what these frequency bands are in detail. The channel bandwidths for LTE. So there is bandwidths defined 1.4 MHz, 3 MHz, 5 MHz, 10 MHz, 15 MHz and 20 MHz. And each bandwidth actually is composed of a certain number of resource blocks. As you can see in this table, a resource block is defined to be 180 kHz each, and the resource block represents the smallest entity for a resource assignment. So a terminal or subscriber can be assigned one resource block or multiples of it. And this is true for uplink and downlink. So 1.4 MHz actually is represented by 6 resource blocks, and so on up to the 20 MHz being represented by 100 resource blocks. Modulation schemes that are available for LTE are QPSK, 16 QAM and 64 QAM, where in the uplink the 64 QAM is optional for the handset to support. Multiple access schemes for LTE are the OFDMA in the downlink, orthogonal frequency division multiple access, and single carrier FDMA in the uplink. LTE supports the MIMO technology. Actually, MIMO, multiple input, multiple output antenna technology, is very essential for LTE in order to support the high data rate and throughput requirements. In downlink, a wide choice of MIMO configurations is possible for LTE, and there's different MIMO modes supported. For example, there's transmit diversity, spatial multiplexing, cyclic delay diversity, and we can have a maximum of 4 antennas as the base station, which is defined in the standards, and also maximum 4 receive antennas at the handset, which is of course quite challenging. In the uplink, a multi-user collaborative MIMO is supported, so several users can share the same resource block assignment. We will see a detailed introduction to the MIMO at a later part. LTE peak data rates in downlink, we can achieve 150 megabit per second with a 2x2 MIMO configuration, which would actually be represented by UE category 4. And we can even achieve 300 megabit per second peak data rate in downlink with a UE category 5, which would stand for the 4x4 MIMO setup. Both values are true for 20 MHz operation. In uplink, 75 megabit per second peak data rate in 20 MHz operation are possible. So please note, the peak data rates are really more theoretical values. They are not likely to be achieved in real-life scenarios, because in real life you have certain cell load, you have certain radio link situations, which will not allow these data rates for a particular user. So nevertheless, the peak data rates are always quite useful to see, because they give you kind of a reference of what's theoretically possible with the system. So this table shows the LTE frequency bands that are specified. The table is actually taken from 3GPP specifications as of March 2009, and they are showing the specified bands for LTE operation. So there will be more bands added in future. For example, there's the work on UMTS LTE 3.5 GHz operation ongoing. So as you can see in the table, the bands 1 up to 17 are defined for FDD operation, and the bands 33 up to 40 are defined for TDD operation. There's some prioritization already defined, so there's a certain prioritization for bands 1, which is the existing UMTS band, band 3, band 7, which is the 2.6 GHz band, and band 13 in the 700 MHz arena. For TDD, band 38 and band 40 have a certain prioritization for real network deployment and for the first commercial deployments. But in principle, LTE can be operated in all these frequency bands. So now let's have a closer look into the OFDMA multiple access scheme and the downlink frame structure for LTE. So what is OFDM? In an OFDM system, the available bandwidth is subdivided into multiple subcarriers, and each of these subcarriers can be independently modulated. So typically you have several hundred subcarriers in a certain bandwidth, and they have a constant spacing of some kilohertz. The figure shows an example for the 5 MHz bandwidth, and you see the subcarriers But of course, you can easily scale the OFDM principle also to higher bandwidths. Like in LTE, you have up to 20 MHz bandwidths. So compare the OFDM transmission with a single carrier transmission, for example for wideband CDMA. Since the multiple subcarriers in OFDM are transmitting in parallel, each one can transmit with a lower symbol rate, thus improving robustness of the technology for mobile propagation conditions. This picture shows the OFDM signal generation chain. So the modulated data symbols, which are going to be transmitted, are first parallelized, and then they are used as input bins to an IFFT operation. IFFT stands for inverse fast Fourier transform operation, which is taking place on the transmitter side in an OFDM system. This operation produces OFDM symbols. So actually we have a conversion from the frequency to the time domain here, and the OFDM symbols are then transmitted in the time domain of an OFDM signal. To each OFDM symbol, a cyclic prefix is appended as a guard interval to protect from inter-symbol interference. So this also means that with a longer cyclic prefix, radio channels with a larger delay spread can be addressed. So for example, larger cell, you would expect a larger delay spread, and therefore a configuration with a longer cyclic prefix would be helpful. On the receiver side in OFDM, you would expect an FFT operation to receive the symbols again and to convert again in the frequency domain. Now, what is the difference between OFDM and OFDMA? We have seen both terms already. So in OFDM, the users are allocated in the time domain only. So in this picture, you see on the y-axis the frequency domain and on the x-axis the time domain. And you see that user 1 has been assigned the full bandwidths, user 2 as well, and user 3 as well, and they are only separated in the time. Compared to that, on the right-hand side in OFDMA, the users are allocated in time and frequency domain. So you see that user 1 is only using part of the available bandwidths, as well as user 2 and user 1, they can share the available bandwidths to a certain extent. So this is actually a very flexible scheme, therefore it is also used in LTE, because you can also, for example, exploit gains of frequency-dependent scheduling. So you could exploit the fact that user 1 has a more beneficial radio link quality in a certain bandwidth area of the available bandwidths. So LTE uses a conventional OFDMA scheme. The picture shows an example for 5 MHz bandwidths, but of course you could also extend it to the other bandwidth values and scale it accordingly. So you see here the representation of the signal in the time and in the frequency domain. In the frequency domain, you see here the subcarriers represented. In LTE, they have a constant spacing of 15 kHz for the regular configuration of the signal. And as we have seen, so you can transmit now and independently modulate on each of the subcarriers. The orthogonality of the subcarriers is also illustrated here. So in terms of the function here of each of the subcarriers, the frequency function, you see that where one subcarrier has a maximum, all the others have a zero crossing, which means that this is representing the orthogonality of the OFDM signal. In the time domain, you see the OFDM symbols transmitted, separated by guard intervals. In LTE, also we have a cyclic prefix as guard interval. Different configurations are possible. We have a normal cyclic prefix with 5.2 microseconds for the first symbol and 4.7 microseconds for the other symbols of a slot. And we also have an extended cyclic prefix for larger cell corresponding to 16.7 microseconds. LTE provides QPSK, 16 QAM and 64 QAM as downlink modulation schemes, so these can be assigned to the UIs in the resource allocations.